Hello, welcome back to the third installment of the video tutorial for section 10.4 in Mr. Billingham's Honors Precalculus class. Today we're going to continue looking at random variables and probability models in part 3. Back in section 10.3, when we first presented the normal distribution model, you learned that about 68% of the population was within one standard deviation of the mean, 95% within two standard deviations, and 99.7% within three standard deviations. This handy guideline says that when data appear to be approximately normally distributed, you can use these rules. But if you want to get more details, you can get it on your grapher very, very easily. We will be using the cumulative distribution function, also known as normal CDF. So do the following. On your grapher, hit second vars 2. Second vars is titled DISTR, which is distributions, and you'll notice 2 is normal CDF, or normal cumulative distribution function. Now, after choosing 2, hit enter. Here you're asked for the lower value, the upper value, and notice that the mean of 0 and standard deviation of 1 have already been pasted in for you. Those are the default values, and that takes you to what's called a standard normal distribution, which has a mean of 0 and a standard deviation of 1. So if I want to find the percentage of the population that's between one standard deviation below the mean and one up above the mean, I would put in values of -1 and 1 for lower and upper. I've gone ahead and done that. We see that the actual percentage is 68.2689 blah 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 between 1 below and 1 above, and I also on the same screen did 2 below and 2 above, and you see it's 95.45 about percent, and from 3 below to 3 above is about 99.73%. So you can use this to get the probability within any number of standard deviations left and right of the mean. Notice that the calculator allowed us to change the standard deviation and the mean if we want. On older calculators, and before that in tables, you could not do that. You always had to convert to a standard normal deviation, normal distribution, using something called a z-score. Now, a z-score measures the number of standard deviations left or right of the mean. And the formula for calculating a z-score is the following. Because our calculator allows us to change the mean and the standard deviation, we do not have to use z-scores. I'm going to show you an example problem, and I'll work it both with z-scores and without. So in this question, we are told that the mean of heights of adult American men is 69.2 inches, and the standard deviation is 2.8 inches, and we want to find first the probability that a randomly selected American adult male is between 65 and 70 inches tall. So first I'll do this with z-scores. I use the formula z is x minus mu over sigma and calculated the z-scores for 65 and 70 inches with a mean of 69.2 inches and a standard deviation of 2.8 to be, as you can see here, and the z-scores are -1.5 and 0.2857. Now I can enter them into the normal CDF model. Here are those two values entered into the normal CDF, and when I hit enter, I get the following. This screen tells me that the probability a randomly select adult American male will be between 65 and 70 inches tall is about 54.6%. I'm going to write that number down so we can remember it. Now I'm going to do the same calculation, but by adjusting the mean and the standard deviation in the normal CDF window and without using a z-score. Notice I This time put in the raw heights, 65 and 70 for inches. Put in the mean as 69.2 and the standard deviation is 2.8. And when I hit enter, it didn't have to do the z-scores. Or you can probably notice that it got this pretty much the exact same answer. It's very, very slightly off. You can take a look and see. And the reason that it's a little bit off is because I rounded the second z-score. So I hope that helps you understand how to use the normal CDF function. I'll use one more example. I'll show you how to calculate over 6 feet tall, and I'll do this one without z-scores. First of all, 6 feet tall is 6 times 12, or 72 inches. It doesn't give me an upper limit, and in theory, a normal distribution goes to positive infinity and to the right and negative infinity to the left, but just goes, like 5 or 10 standard deviations to the right, and you'll definitely be so close you won't be able to tell any difference in the answers. So here's what I chose to do. So to do above 60 feet tall, which is 72 inches, I just did 72 up to 100 inches. And that is so far above the mean, so many standard deviations, that the probability that I'm losing in the tail is tiny. You could do 1,000 if you want, but it's not necessary. In the second screen, you can see that the probability of a person being above 72 inches or 6 feet tall is about 15.9%. The last one, under 5'6", well, first of all, we have to convert 5'6" to inches. That's 66. So I'll just do from 0, nobody's 0 inches, but that's way to the left, from 0 to 66. And here's what that screen looks like. Here we can see that the probability of somebody being shorter than 5'6" inches tall is about 12.65%. So that's how you use the normal CDF function. We've been using z-scores, or their equivalents, which include lower limit, upper limit, mean, and standard deviation, to find the probability of the occurrence of some event. You can use inv norm to reverse this process. So in other words, this time we're going to type in a percent, and it's going to figure out what the value of the variable would be that would occur with that percent. So here's how you do it. Under second vars, which is DISTR, choose number 3, inv norm. In the second screen, you see they're asking for area. Now, the area under a probability distribution is always equal to 1 and is equal to the total probability. So when they say, what's the area, for instance, in this one, and I'm saying 90.90, I'm finding, in a standard normal distribution with a mean of 0 and a standard deviation of 1, where would those people lie who are within the 90%, starting at the left tail, which technically is negative infinity? So let's take a look at the next screen. So let me interpret the result. This is saying in a standard normal distribution with a mean of 0 and a standard deviation of 1, if you want to trap 90% of the population, you're going to be below 1.28155 standard deviations above the mean. So that would look something like this. You can see from the little sketch that to be 90% of the population, you have to be below 1.28 standard deviations above the mean. Notice also that the inv norm gives us the chance to put in our own mean and our own standard deviation. So we don't have to accept the z-score approach. But let's do both. So here's a problem to work. We're asked 2 questions here, and again, it's based on the theory that the mean of American male heights, adult American male heights, is 69.2 inches, and the standard deviation is 2.8 inches. In A, they're saying the shortest 20% of Americans are less than what height? So here's how I'm going to do it. I've called up the inv norm function, and I've put in for area 0.20, which corresponds to 20%. Let's see when I hit enter what the result is. it tells me the result is negative 0.84 blah blah blah, which means 0.84 standard deviations to the left of the mean. Now, since z is x minus mu over sigma, where z is the z-score, x is the value that we're interested in, mu is the mean, and sigma is the standard deviation, we can solve this for x, getting. So the screen on my calculator, that negative 0.84162, that is the z-score. If I take that expression, multiply it by sigma, which is 2.8, and add mu, which is 69.2, I'll get the answer to the question. And I can do that right on my calculator. Notice how I used answer times 2.8, which is z-score times sigma, plus 69.2, which is the mean, and I get an answer of 66.843. So that answers question A. The shortest 20% of American men are less than 66.8, which is 5 foot 6.8 inches. Now, how big are the tallest 1% of American men? I'm going to do this one without the z-score. Here's what I've populated the InvNorm screen with. For area, 99%, because I want 99% to be below my height, so I'm in the top 1%. I have, of course, the mean is 69.2, and the standard deviation is 2.8. And when I hit paste, here's from the screen, you can see that the tallest 1% of American men are greater than 75.7137 inches. Now, 72 inches is 6 foot, so they're just a little bit below 6'4", 6.3.7 inches in height. I hope these examples help you understand InvNorm as well as normal CDF. Play them over and over again and look up how to use them on your calculator. You can use your calculator for doing the homework, by the way. So, how okay is it for us to use a normal approximation for binomial distributions? Well, first off, let me say that a binomial model and a normal model are quite different. Binomial random variables are discrete. When I toss a coin, it can really only have a whole number of heads. Normal random variables, on the other hand, are continuous. Heights can, and as you grow, they must take on every possible value from your birth height to the height you attain as an adult. Binomial random variables are bounded. In n trials, the number of successes must be a number between 0 and n. But a normal model extends without bound in every direction, or left and right anyway, from negative infinity to positive infinity. Despite these differences, a binomial probability distribution based on a sufficiently large number of trials is approximately normal. Figure 10.26a shows the binomial distribution for the number of threes seen in 10 rolls of a fair die. Because it's skewed to the right, a normal model is not appropriate. In figure 10.26b, the number of rolls of the die is increased to 100. The superimposed normal curve is barely discernible, showing how good the approximation is. The number of trials required for a normal model to approximate a binomial distribution depends on the probability of success. If p is 0.5, the binomial distribution is symmetric, an important attribute of normality, so a relatively small number of trials is sufficient. But if, as in the case of the die, p is far from 0.5, it's 1/6, the binomial distribution will be skewed, and many more trials are needed. In one of the exercises, you can explore why the following rule of thumb works. Here's the success-failure rule. This tells you when it's appropriate to use a normal distribution to approximate a binomial distribution. If you expect at least 10 successes and 10 failures, and that is that n times p must be at least 10, and n times q, or n times 1 minus p, is at least 10, then the binomial distribution for the number of successes can be approximated by a normal model with mean equals NP and sigma equals square root of NPQ. So let's look at an example. At the beginning of this section, we posed a question about coin tosses. If you watch a person toss a coin 100 times and get 66 heads and only 34 tails, should you be suspicious that the tosser is cheating somehow? The distribution of the number of heads is binomial, with n equals 100 and p equals 0.5. Because we expect NP, or 100 times 0.5, is 50 heads, and NQ, or 100 times 0.5, equals 50 tails, both of which are at least 10, the distribution is approximately normal. This normal model has mean, (50) and standard deviation, (5). 6 heads is more than 3 standard deviations to the right of the mean. So it doesn't prove that the tosser is cheating, but you'd have every right to be suspicious. For the last example, we'll go back and visit the chimpanzee in question. So remember the chimpanzee guessing at 105 multiple choice questions, and each one has a single answer. How high a score might we expect a lucky chimpanzee to be able to get? Well, let's think about the stuff. We would expect NP, or 20, successes, and NQ, or 80, failures. These are both more than 10, so a normal probability approximation should work quite well. Let's calculate what the mean is. Well, the mean is NP is 20. And how about the standard deviation? Well, the standard deviation is given by sigma equals square root of NPQ. That's square root of 100 times 0.2 times 0.8, which is square root of 16, or 4. Now, if the chimpanzee was 2 standard deviations above the mean, which only happens about 2.5% of the time, he could get a score as high as 28. If he went 3 standard deviations above the mean, which happens like 0.15% of the time, he could get to 32. But for him to get a score that was passing like 65 or 70 would be so unlikely that you would just know that someone's helping him or there's some trick going on. So that concludes the material for 10-4. I hope it's been enjoyable. I've enjoyed it. I wish I would be teaching it to you in class, as I've told you many times. I hope you're all staying well, finding things to amuse yourselves, but also getting your work done. And I'm going to try and reach out to you tomorrow. All right, bye-bye.